Hello, well, everyone. This is Shadow Drake, and this video is going to be a video talking about the phase change mechanics that you will see in Stationeers. I will say that because this is a mechanics video kind of laying out how gases and liquids work and all of the resulting math and science behind it, it's going to get very technical, very sciencey. So I will do my best to keep it interesting, but I will definitely split it up into parts. First of all, I will just give you all the science straight up. Teach you what is phase changes, all the mechanics, how to read phase change diagrams, all of those details, and that will be the meat. But hopefully, it will be useful information you can come back to. After that, I will share with you all the materials, well, all the kits that you will need to use to properly move around gases and liquids from your many pipe systems. Then after that, we're just gonna do some experiments. This will hopefully help you to see how the phase change mechanics work with the science involved and how our different devices can move gases and liquids. And I can give you some tips and tricks, things that will help you out as you invariably will deal with this as you start pressurizing tanks and pipes. And I will close it off with one little bonus for how to cleanse your base from all of the water you may have accidentally released in there. Alright, without further ado, let's get to the science. Alright, so first of all, I'm gonna say that in this, bring up your Stationpedia F1, you can pause or continue the game up here. I'll just get that out of the way. So, phase change. Now, if you recall, water is probably the easiest thing to work with as background, or probably the most familiar substance you know to phase changing. Matter can exist as either solids, liquids, or gases. The thing about solids is that matter is basically rigid. It's all bonded together. Liquids is not as rigid. There's still some bonds, but it allows some flow to happen between that. And gases, there's no real bonds between the substance, and it just freely roams, moves around the system. And with that, you basically have temperature that goes along with it. And now, temperature is a measure of how much kinetic energy is in that substance within its own atomical structure. So just short end, it plays a crucial role with whether something will want to be a solid, gas, or liquid. And so let's go back to our water. Um, you know that water freezes at less than 0 Celsius and will boil at over 100 Celsius. Now, the thing about that though is that gives you a sense of where water will exist as a solid, liquid, or gas. But even knowing that it boils at 100 Celsius is a little bit misleading because what isn't known or what is understood is that this temperature point is under 1 atmosphere of pressure or 101 pascals of pressure that is native to our planet. Excuse me. So, with that, it is impossible to tell you how you should store or keep your gases in the game because you will always be pressurizing them or keeping your environment in something other than 100 pascals, 100 kilopascals, including water. And so our Stationpedia thankfully will provide you all the information you know. Just open it up, go to gases, that'll list all the gases you have. You could also search for them. So let's start with water. So with water, we get our little information, and I'll just go briefly how to read this information. And it applies, now this information applies to water whether you look at it as a liquid or as steam. That information will be the same, so it doesn't matter which you choose. Now, we'll go over this information. The specific heat is how much joules of thermal energy it takes to heat 1 mole or cool 1 mole of in this case, water by 1 Kelvin or 1 degree. So as you can see, it has a pretty high specific heat, at least compared to volatiles, where volatiles doesn't have as much. That's why typically you hear it mentioned that water is really good at retaining heat or resisting heat changes. The latent heat, this is very important information when water is doing phase changing. Uh, Phase changing would be condensation or evaporation. Condensation will occur when you have gas becoming a liquid, and evaporation is the other way around. Now, the science behind that you will need to know is that this latent heat is 8 kilojoules per mole. So it completely depends on how much is condensing or evaporating. Now, when a gas condenses, it will release a lot of heat. To go from a higher energy state, a gas state, to a lower energy state or liquid state, most of the all the molecules, the chemical composition of that gas will have to release that extra energy, and that is noted by this 8 kilojoules per mole. So as you see water condense, you will release that much heat. Its surrounding will warm up pretty significantly. On the opposite end, for evaporation to occur, you have a lower energy state going to a higher energy state. It needs to take in that much energy to complete that transformation. So when you see, in this case, if water will evaporate, it will take up 8 kilojoules of energy from its surrounding, rapidly cooling it down. This is partially one of the reasons why crushing water ice in an ice crusher, you run the risk of potentially freezing your pipes and busting them. Uh, Especially if you set your ice crusher to 0 or 273, because you have water that's already really close to freezing trying to evaporate, and it will not take much more to hit freezing. Speaking of which, moles per liter. It doesn't say that. That's probably the only information that isn't populated. Let me check others. Yep, moles per liter. This information is only populated for the liquid, so I stand corrected. And it just tells you how many moles of that substance is in 1 liter. Next up, we're going to go with freezing temperature. That one's very simple. Freezing temperature, 273, 0 Celsius. You go below that, boom, it freezes. Doesn't matter whether it's a gas or a liquid, although apparently there is frozen liquid ice and frozen gaseous ice. We can argue about that later. But if any gas goes below its freezing temperature, it'll start freezing. And you can see that with many different gases, they will have different freezing temperatures. So this is very vital information to look up, especially if you are planning on doing cooling for a planet or like Europa or the vacuum moon or Mimas or the moon, where you can just radiate heat into space. You need to be extremely careful about how much thermal energy you release and what the temperature of the gases will be. Uh, Now, water will have this boiling temperature, as you recall me saying. 100 Celsius at 100 kilopascals is the boiling temperature. Uh, you will not see that information on any other gas because, quite honestly, there's it's never gonna be a liquid at 100 kilopascals. The only one that can do that is water and stationeers. Let's see. Now, these two bits of information, minimum condensation pressure and max liquid temperature, are kind of useful. I It helps give you a lower limit for how much pressure you need to begin to have a liquid. But in my opinion, probably the most useful one would be the max liquid temperature. As you can see, water you can keep having liquid water in stationeers until you hit 370 Celsius. Once you get water above that temperature, it's just going to be a gas forever, regardless of what pressure. The reason we have 6,000 kilopascals or 6 megapascals listed is because your liquid pipe network can only be pressurized to 6 megapascals, and then they start taking damage and break. So your freezing temperature and your max liquid temperature is very vital information to know when working with the gas. Um, for demonstration purposes, we will be working with nitrous oxide. And as you can see, it freezes at -21, and my max temperature is 158 Celsius at 2 megapascals. So NOS is a little different, but nearly every other gas will be listed for 6 megapascals. So now that we've gotten through this information, let's go down to the phase change diagram. This may look confusing, but it's actually fairly simple. First, I'll point you out to the log scale and use Celsius or not, and this just changes how the graph looks. Personally, I like to use the log scale so that I can see where my minimum is, but all it does is just kind of simplify and make it a nice little curve or a nice little line, depending on whether you like to see pressure in a logarithmic scale or just a straight linear scale. And then you have Celsius or Kelvin. The graph will adjust automatically, -272 Celsius or Kelvin. Now, which ones you use is user preference. Kelvin is used in a lot of the logic gates, a lot of the logic system in Stationeers, but most of the time Celsius will be the most easily referred to. Alright, so with that, how to manipulate your graph, let's take a look at it. This solid blue line denotes your freezing temperature. As you can see, for water, that's 0 Celsius. So this solid blue line is 0 Celsius. You will have water freeze to the left of this line. So every single point here, any water will begin freezing. So that's simple enough. And now, continuing on your curve, every point above this curve right here is where you will have a liquid, is where that gas or compound will be a liquid. And finally, every single area outside of that curve on towards the bottom is where it will exist as a gas. So what that means to say is, if you have water at 50 Celsius, which is approximately here, and you're pressurized to like 5 megapascals, you'll land right here on this graph, which you will know that water will always be a liquid. Any water you introduce to that heavily pressurized pipe network will immediately condense, if it hasn't yet, and turn to a liquid. Or you can safely inject that pipe network with liquid water and be assured that no evaporation will occur. On the converse end, if your pipe network is not very pressurized, you can inject steam to keep it as a gas until you hit a critical pressure threshold. And so now comes reading that critical pressure threshold. As you can see, there's a small little cursor that you can see as I move left or right on the mouse. And as I am moving that cursor, you will see a temperature and a pressure. This is the exact points for the temperature pressure curve that you need to be careful when considering if this gas or compound will go through any phase changes. If I were to just point it at 100 Celsius, that's going to get difficult. You'll actually see that 80 kilopascals is what I need before a phase changes. That's interesting. That's a little bit different from that. But barring that, every single gas liquid on Stationeers will have that curve, and they will all look different. And it is all completely based on the properties that developers have designed for this game. So key takeaways from this. As you're going to begin to store your gases under high pressures and temperatures, if you are heavily unfamiliar with what it's going to do or what you expect to happen, just F1, pause it, look up the individual properties, see where you're going to have problems. In shorthand, pay attention to the freezing temperature and the max liquid temperature, and that already gives you a good estimate. Like for example, for Mars, you can see it's nighttime already, -35 Celsius. Which gases is this going to be a problem with? Uh, Definitely a problem with nitrous oxide, because that it that temperature is too low. It will freeze. It'll land here. Other problems is water, 0 Celsius. But if you take a look at it, pollutants have a low freezing temp and a high liquid temp. So you're gonna start to see liquid pollutants if you add quite a bit of pressure. So if we look it up, negative 35 Celsius. So you can see if the pipe network is at least 2,733 kilopascals of pressure, you're gonna see pollutants condensing. Uh, Carbon dioxide is a very tiny graph, but it follows the same structure. See, even though this curve is very small, you will see that carbon dioxide will condense at that temperature at a lower pressure than pollutants. So hopefully this can at least shine a light as to why you may be experiencing pipe bursts from liquid condensation in your gas pipes or freezing temperatures. Always refer to this phase change diagram to kind of get an understanding for how how the gas will behave under various temperatures and pressures. Now, you could try to bypass all of this and store all your gases at high temperatures to never have any liquid issues. But as you will see, to do that with pollutants, you need at least 152 Celsius. It is up to you to decide if that is a useful storage, a useful medium of storage, or to just bite the bullet and store it all as a liquid and grab what you need. So with that, that is the major, that's probably a lot of the science involved with how to read this diagram and what happens with your latent heat and specific heat. Uh, One thing I will mention is that when phase change happens, it is the gas and compounds in that pipe are desperately trying to reach equilibrium. Uh, Remember how I said as a gas condenses, it will heat up its medium. So what that would end up doing is subtly increase the pressure of that gas pipe network. Because by the ideal gas law, PV equals nRT. Higher temperature means higher pressure because the volume will stay the same. So you'll get a little extra pressure, which will force a little bit more condensation, but there will eventually come a point where the whole system equalizes and all of your gas will be a liquid, or you will be in a steady state where you have constant evaporation and condensation. And that's when your pipe network is finally stabilized and hopefully it hasn't broken. You have something to take care of in the aftermath. All right, so that concludes most of the side. Oh, one last thing. Uh, when phase change occurs, no thermal energy enters or leaves the system. You will see temperatures increase or decrease appropriately, but so long as you are not purposefully adding or removing thermal energy by either adding more gases or pipe heaters or anything, you will see that that temperature at the end will come back to be the same once you let all phase change complete or revert. And I'll show that with a later experiment. So with that, let's move on to our materials. Okay, with the science all done, let's look at what kits we have available to us for moving gases and liquids around. Now, while you have regulators and volume pumps of the gas and liquid variety, I'll particularly really only focus on the ones that move gases and liquids around between the two networks. And so here I have them listed in the wall. From the pipe valve kit, you have condensation chambers and expansion valves. Condensation valves, my bad. Condensation valves and expansion valves are both passive systems. They will only move liquids around. So condensation valves will move liquids from gas pipes to liquid pipes. Expansion valves will do the opposite, move liquids from liquid pipes to gas pipes. Straightforward. Since there's no data attached to this, this could be problematic for automation if you're gonna be moving systems. So be extremely careful with expansion valves because they really will just flood your liquid pipe network. All right, next up, from the pressure regulator kits, the normal pressure regulator kits, you have an option of pressurant valves and purge valves, and just like the other two, these both require power, so they can be automated to a degree. Pressurant valves and purge valves, however, move only gases from one pipe network to another. So pressurants move gases from gas pipes to liquid pipes, and purge valves do the opposite, gas pipes within a liquid pipe to a gas valve. Uh, One of the major reasons you want this is because you do need to pressurize liquid pipes to prevent unwanted evaporation. This would be extremely helpful, for example, storing water. If you have a well, completely empty pipe network, any liquid water that hits that pipe network will eventually will begin evaporating to add atmospheric pressure into it. And you recall evaporation means cooling, which means eventually freezing. You can bypass that by just pre-pressurizing that pipe network with any pressurant gas so that any liquid water or any liquid anything that hits a liquid pipe network will happily stay as a liquid. Um, Purge valves is the opposite. Since it just extracts gases, you'll only need to be careful to make sure that you have plenty of pressure and gas so that removing those gases will not cause an issue with evaporating liquids. And then finally, from the liquid drain kit, I'm mentioning this because it's a tool that's needed. You have passive liquid drains, liquid inlets, active liquid outlets, and then a liquid drain that can attach to pipes. This is particularly for moving liquids into or out of your atmosphere. For the liquid segment, this passive liquid inlet, as you can see, pressurize this pipe network because what it does is it tries to capture liquids in the surrounding atmosphere, and in doing so, it equalizes the liquid pipe network's atmosphere to that of what's outside. This is one way to remove liquids from the air, but it can also be used to help purge extra or evaporate liquids and let it mix with the air. Um, Active liquid outlet does the same thing, except it only lets liquids out and it requires a power connection. And of course, the pipe liquid drain will just drain liquids out of a pipe just passively. So with that, those are the three major tools you'll probably end up needing to move gases and liquids around. And so now we'll just start with the experiments. Alright, now let's get started with the mechanics. Okay, so now what I have here is I have a tank of nitrous oxide. It's my mixing tank for high density fuel, or and as you can see, it is at 17.9, almost 18 degrees Celsius. And I have a little pressure regulator that is filling these 10 insulated pipes with 600 kilopascals. Now, if you recall what I said about the ideal gas law, PV equals nRT. So I am going to manipulate gas pipes, liquid pipes, pressures, and all of that stuff to force phase changing to occur and show you exactly what happens. So, whoops, let's pause first. So, my tank is about 18 Celsius, and as you can see, I don't expect to get any phase changing, or in this case, condensation occurring. Come on now. Alright, I guess it can't hit 18 exactly, but alright. So somewhere between 1020 kilopascals. That's where I would expect to see some phase change occur. Now, I got exactly 600 kilopascals in this pipes. So what I'm going to do is I'm going to remove half of the pipes. This will in turn double the pressure. And once that happens, we should see some of these nitrous oxides condensing. 4, 5. Alright, so we have half the volume in here. And as you can see, the pressure did double. And as you're watching the symbols, by the left one is gaseous NOS. You saw a little teardrop water icon. That told you that it was condensing. And on the right side, you see liquid NOS. And so that's all the liquid NOS I made. And as you can tell, it settled at 1.1 megapascals, 30.7 Celsius. So if we looked at that in our phase change diagram, let's go to 31. Yeah, you see that's about right. The graph may be a little bit off, but that holds about true. Almost 1.1 megapascals, at roughly 31. And as you notice, it did get warmer. Now, one of the reasons I'm using insulated pipes is because no heat energy can transfer in or out. So this is purely, this NOS getting warm purely happened due to the phase change, the latent heat of condensation. So now let's see what happens when I re-add these segments. That means I will cut the pressure down, and you should see it evaporates. Now, as you see, for my liquid NOS, you see these little wavy symbols. That means evaporation is occurring. Now, recall that with the science stuff, when phase change happens in a closed system, that means no heat energy can enter, escape, or the molecular, how much is in there, doesn't change as well. It will settle back to the original temperature. So I expect to see it settle at 17.9 Celsius once all the liquid NOS evaporates. I see I still got a little bit left. Give it a little bit more time. And you can see I'm already basically at that temperature. There we go. 17.9 Celsius, 600 kilopascals. I'm literally right back where I started. This is to show you that phase change does not generate or lose thermal energy in an enclosed system. This will be the primary reason why phase change device heating and cooling works. Because all you're really doing is moving energy around with condensation and evaporation. So, now that you've seen me force phase change occur, how can we manage it around? So let me go on ahead and force it to condense again. Whoops. Oh, that's not good. Get out of there. 4, 5. Let's fix that hole. Okay, so let's see. Got our liquid NOS. We got some pipe stress, as you can tell. This pipe stress is completely dependent on how much liquids compared to your capacity there are. If I were to keep removing segments and have less capacity in liter, less volume, you will see that my stress will keep going up. But also what I am doing is I'm also compressing the gas, forcing more to condense, higher temperatures, more stress. If I were to remove more of these, I believe I should get to a point where, yep, almost at 100. I should hit 100. Just barely didn't hit 100. Alright, so you could be at this point and you will not have any damage to your pipes. When you hover over your pipes, when it is this stress, well, it's just going to say there are liquids in the pipe. Now, if I were to remove this last section, you'll hear the groaning sounds. You'll see on my hood there is damage occurring. Damage due to pressants, condensation is happening. Very, very stressed. These pipes are stressed. They will eventually break. So let's re-add these segments. This damage is going to stay until either the pipe is fixed or you just remove it and reapply it. Alright, back to original stuff. Now recall, liquid networks can hold liquids better. Now, if I were to put this insulated pipe, it's absolutely empty. I will have a problem if I just put a condensation valve and allow this 0.8 liters of rough point, this little bit of liquid, 0.078 liters, to come here. Because what's going to happen is, recall through phase change, where's the temp? 30? 31? Recall that I need to have, come on, 32, whatever. I need to have close to this amount of pressure in my liquid pipe network. Otherwise, any liquids that go into that pipe network are going to fall in this part of the phase change curve. And this means gas, which means evaporation will happen. And recall that I said that if you have evaporation, you get a lot of cooling. So if I were to do that, my NOS is evaporating. I am cooling down. And remember that negative 21 Celsius is the freezing point. I don't think I will hit that. I might not. Yep, I'm going to hit it. Alright, there we go. Freezing point. And groaning. Lot of damage. Look at that. That is really creeping up there. Yeah, that's going to be unsalvageable. Yep. And that is because of ice. Ice will break your pipes really, really quickly. This is not going to be salvageable. It's going to break. So let's just show a break. 195, 96, kaboom. Yeah. Alright. It broke. And as you can see from the hood, this pipe is destroyed because liquids or gas is freezing. And as you saw, they were freezing. This is why you will want to pre-pressurize your liquid pipes. Alright, so let's get my hand drill, remove this. So what if I pre-pressurized my pipe network? So from your regulator, you can grab a pressurant valve. Pressurant valves are going to be needed to pre-pressurize a gas network. Let me just build sloppily. I mean a liquid network with gases. Let's just build horizontally. Now it'll work. And let's put a condensation valve. And you know what? I need to... Actually, no, I can keep that there. Need some power. Alright, so what will work? Let's see. What is my temperature here? It is 31, 1.1. So let's go with the next experiment. Before I pressurize this, let's say you want to add a certain amount of gas to this pipe. If I were to turn this pressure regulator to, let's just say, 1.5 megs, turn it on. So what's going to happen is it's going to attempt to reach 1.5 megs. But recall also that doing that, I am getting condensation. I am generating liquid NOS. So what's happening is I am pushing some of my NOS into this pipe network, and I am compressing it. Now that pressure regulator is going to make me hit 1.5 megs. 1.5 megs means that I need about a temperature of 90 to 93 Celsius. And that'll be the critical point where no more condensation or evaporation should occur. Let's see, I'm still getting 1.5 megs. I literally forgot 93. No, stop. So you see this temperature should approach 93. I might actually break my pipes. So let's pressurize this liquid pipe network with 1.5 megs. Oh boy. I picked too big of a number. Well, I can just add more volume. Adding more volume should remove the stress, but I slowed down the process. Okay. Mistakes. Oh. Right. I also forgot that I am now pressurizing this network to 1.5 megs too, which means I have some liquid loss. And so this is a good example of when you try to pressurize pipe systems, you need to be wary of what temperature and pressure they correspond with each other. NOS very easily condenses. I chose 1.5. Really? Once again, I am stressed. Alright. So now that I have my 1.5 megapascals, I know the temperature is going to climb to 93. But as you can see, with liquids being happy, I can just turn this valve on. All my liquids are going to come back. Look at that. No more stress. It's all going into my liquid pipe network. Now, let's change you to a purge valve for the next experiment. And let's add an expansion valve. Now, an expansion valve will push only liquids. I can turn you off right now. So 1.5 megs, 90.5 Celsius. If I turn this off, you see that I have roughly 2.97 liters of liquids in here. In order to turn this expansion valve on, this is going to completely empty out. And it is now in the liquid pipe network and stressing it the heck out. This is why you have to be really careful with expansion valves, because you can very easily just push every single liter of liquid into your gas pipe network. So let's drain it of liquids, and let's go with the purge valve. Let's set this to 1 meg. Just be gentle with it. Now recall how I said a purge valve will empty gases out of a liquid pipe network. Now with phase change, that means that if I lose pressure, some of this liquid must evaporate to maintain the pressure. But in doing so, I'll cool down the whole system, slightly less pressure, more evaporation, until it finally hits a steady point. So, let's drain this. Alright. See, we're at 1 megapascal. Some of my liquid NOS is evaporating. And is also cooling down. Now, 1 megapascal is approximately 16 Celsius. So this is just going to keep evaporating until the temperature hits 16 Celsius. Once it hits that point, it's going to stop. So I'm just going to leave that running for a bit. And we're going to come back to it in a moment. So right here, I just took some Martian air when it was warm outside and just brought it into this pipe network. As you can see, I have liquid pollutants. This would probably be your first experience dealing with phase change if you are completely unaware of it. You'd probably be doing something simple like grabbing air from Mars with the intent to grab probably oxygen or CO2 for your plants. And if you walked away and just let it keep building up pressure, well, we have liquid pollutants now to deal with. If you are not watching this, you'll get a lot more liquid pollutants. And then, as you saw before, this pipe would burst. Let's see where we're at now. Oh, we're getting really close now. I have bad memory. Yeah, 15, 16 Celsius. Alright, as you see, the temperature got down to roughly where I said it would be. Uh, Less and less is evaporating. Once this hits zero, then it's stable. Now I have noticed that this graph is slightly inaccurate compared to what actually happens. Uh, that might be a little bit off-settling, but for the most part, it should get you close. It should hopefully arm you with what you need to get through that, to do all your related phase change stuff. Now recall that when I was pressurizing this pipe, my NOS was condensing due to pressure. If I were to inject some of this NOS into this pipe network, you will see that the NOS will also immediately condense. Why? Is because this is very heavily pressurized. So that's almost done, fully evaporating, but this will at least help you see how to move gases around, how to pressurize pipe networks, uh, the the and definitely building condensation valves to drain liquids from your pipe network. Uh, and also the dangers of an expansion valve when you're connecting it to a pipe network. And as you saw, pressurant valves are really good at pressurizing a liquid pipe network, and the purge valves instead only draw the gases out. If I were to pressurize this liquid pipe network with any of these gases, um, you will see that the rest of this NOS will condense. And if I were to use a purge valve, I would only be getting the Martian gases that would be pressurized in here. In fact, I would have to use an expansion valve to get purely NOS, and that leads to difficulties. I've found that if you want to have a pure tank of just this stuff, uh, filling it with just NOS will probably be the best bet, so that you can control how much you get out with a purge valve. But that doesn't mean that you could fill this with nitrogen. Don't do volatiles or oxygen. It just means you have to work a little harder to get purely the NOS if you need the NOS. Alright, so with that, let's go on ahead and drain my tanks. So hopefully those few experiments showed how to move gases and liquids around. So now let's get to some other experiments that I can show you, purely with vents and passive liquid trains. So I'll be right back. I gotta make some inline tanks. Alright, we got some utility pipes now. So let's add some volume first. So this part, we're just going to have build some different ways to drain some of these liquids out. So I added this to get a lot more capacity in here. Give me some wiggle room for this. Probably the easiest thing to do would be to just add a condensation valve. Oh, come on. Condensation valve. And let's just go on ahead and add liquid tank. So while this could work, and I can just store some of my any liquid pollutants that give out, what if I actually don't want it? What if I just want to drain it? Well, we got several builds to go with that. Now, we could use a passive liquid inlet, and let's turn on the system and start pressurizing. So now we're generating liquid pollutants and liquid CO2 to boot. And the stress is definitely building up. And as you can tell, my liquid network is filling up. Some of it is evaporating desperately and coming out our passive liquid inlet. The more volume you have, the easier it is for you to kind of expel this. And as you can see, I actually stabilize. I'm stabilized the stress and actually dropping. Ooh, that's really close. -10. And if you check the, let's see. So yeah, this is one way to actually get rid of liquids that you don't want. See, my pipe network is almost completely filled up with stuff that I could want. Uh, Very heavily pressurized. And all I have is a bunch of CO2 and pollutants to get rid of that. Now, one thing about a power vent is it does not stop. It literally does not stop. Oh boy. Let's not break my power vent. Yeah, alright. We saved it. We saved our... And as you can see, all of this evaporation is actually going to damage our liquid pipe tank. Oh, my inlet is about to break. Ha! It just deletes. That's interesting. Alright, let's salvage our tank. And now we have a really filled up tank with just CO2, nitrogen, and oxygen. Let's go ahead and rebuild that. And looks like I'm going to need to borrow some of you guys. Alright, but what if I instead use the one-way valve and have that? This should at least somewhat protect my pipe network from being damaged. Let's see. Now this is gonna be a pretty interesting solution that I have used in Vulcan. For example, having a one-way gas. Oh, come on. Coming up here. Maybe just one inline tank. Where's my cowl? And a pipe cowl. Woo! Alright. Alright, let's see. Now let's turn on the system again. With this setup, I should be drawing Martian air. This one-way gas valve will push a lot of excess air out this little cowl. And it's doing too good of a job. Let's fix that. Oh, come on now. And turn back on. Alright. Now, as you can see, we're generating liquids. They're going to be coming in here, which are then going to be pushed through this one-way valve out through this liquid inlet. This can be something that you can use in Europa. Since it'll be purely oxygen, you'll actually just be condensing oxygen. But because Mars has such a low trace amount of pollutants, what I am doing is this latent energy due to the pollutants is actually kind of not even really being used at all. In my atmosphere, I am 16.3, and in here I'm a little colder. But as you can see, this one-way gas pipe is allowing excess pressure to come out. And if you have enough condensation happening in here, it should warm up this pipe to give you a new temperature threshold for something. You can use that as a stable temperature source for phase change loop devices, or to at least begin some form of heating or cooling. Atmosphere world is 18. And as you can see, while I am technically building up in liquids, some of them are getting expelled out here. And my stress is very slowly climbing, but it's fairly stable. If you really want these pollutants, of course, you could have made sure that this pipe was pre-pressurized, and then you'll have a bunch of liquid pollutants. Let's stop it for now. One other thing that you can do let's see, what is the best way I can go about this? Remove that. And actually, put an expansion valve. Why is that in a terrible position? Is that right? Yeah, there we go. And just for safety, I'll add one of these and another pipe cowl. Let's see how this works. Depending on how much liquids you're generating, either the passive liquid drain or this really weird looking configuration would work to gently expel the gases and keep you at a good, decent capacity. Because ideally, if you're going to build a system where you're drawing air to generate liquids and expel the liquids, because all you need is the thermal energy, or if you need this liquid for cooling something down, it completely depends on how you intend to use it. But this could be an interesting thing to do on a planet. And as you can tell right now, the world is at 20 Celsius. My pipe network is at 20.1. In Europa, you could use this to get some oxygen and bring it from what, roughly negative 150, and instead have it be at negative 130. It could be a good start. For Vulcan, you'll have a lot of liquid pollutants, and while the pipe network that condenses your pollutants will get hot to like roughly 150, your liquid network is going to cool down and be at roughly 70 Celsius. That is something that you can work with to cool down or begin cooling down some of your thermal tanks in Vulcan. So yeah, this is one way that you can draw in a bunch of atmosphere to force condensation, and then you can either use the hot pipe network or the liquids that are generated to cool stuff down. And this is, other than the power vent, this is a fairly passive system to kind of mess around with the phase change system. So this is just something out to show. Hopefully this could be used in some way. But yeah, That's what I got for face change, and now we'll hit the bonus stuff. Alright, welcome to the bonus. How many of you just came back from a hard day of mining with your trusty pickaxe, and you see your indicator, you need some water. And so you decide, well, first of all, let's pressurize my base a little. I got some oxide, got some water ice from my crusher. And so you're like, all right, let's pressurize. And you kind of slip up with your mouse cursor or something, and you accidentally drop your water ice. And suddenly, you are now living in a sauna. And as you're desperately trying to grab this, you now have this unfortunate thing of water in your base. No one? I'm sure this has happened before. And so while you ponder your life's problems with misty, steamy air, you now wonder, how am I gonna clean this up? That's quite a lot of water in the air. It's spreading. It's a problem. Well, fear not. We can put our pickaxe away, and we can use some of the tricks that we have learned with our liquid drains to get it. So first of all, first thing we want to do is get a passive liquid inlet. And probably a inline tank. And as you can see, that's cleaned our air. Or it is in the process of cleaning it. Whew. But now you have a problem. You have this odd mixtures of gases in the pipe network. And your liquid pipe network is either going to be pure H2O or just have nitrogen or whatever you pressurize this with. Now, if you were someone who has not been cleaning their base regularly and you have some pollutants or volatiles, that would be a problem because that would mean you can't make this lovely water bottle system work anymore. So how do we fix this? How do we only pass water, for example, to our pipe network? Well, here is one way to do it. Let's build a gas inline tank. And this is going to need, first of all, let's not build it like this. This is going to need an atmosphere. Alright, now that we build a cowl, we got an atmosphere, we can remove it. Why do we need an atmosphere? Because remember, we do not want to let water evaporate. Sure, it might be 20 Celsius, but what happens if I just put empty water in here? The last thing we want to do is freeze it and break a pipe, and now you still have to clean up more water out of the air. So, we can build an expansion valve. Because as you remember, expansion valves will only push water out. Now, if you did what I did and completely forget about the stress of this system, we got a little problem. So let's vent this out. Whew. No more stressy pipes. But wait. We have one more thing we can do. We can make condensation valves. So let's build a condensation valve. And go on ahead and connect this. I need a normal liquid pipe. Yeah, beep beep. Alright. Now remember, condensation valves only pass liquids. See, I have not tainted my water supply with any normal air. And now, I am cleaning my base of the horrible mist and pushing all that liquid water back into my tank without contaminating it at all. So now next time you go mining and you decide to just drop a bunch of water ice, no fear, because you have a really small and simple system to just clean the air of water. Alright, hopefully this will help in some way. Ooh, wow, I dropped my temperature. Hopefully this will help out if you ever make this mistake, or you have somebody come in and drop water ice in the air. Alright, this is Shadow Drake. I hope you have learned... well, I hope you put up with all of the math and all the craziness with a face change, and hopefully you can... it is not going to be a daunting or scary thing to deal with. Have a good day, and good luck with all your engineering endeavors. Goodbye.